And that's by y is x in x bar. That's reflexive law. So that's note 1. Note 2 is that x bar is also equal to the set of all y in the element of x such that y is related to x. Okay, why are these two sets equal? Why am I allowed to just flip that around? That's all I've done. That's the symmetric law. And so I will use this all the time. Okay? So we'll be able to switch these things, and we'll have to do that in the first proof that we do, switch the order of things. But that's automatic because of the symmetric law. So we will use both of these facts in what follows. Okay. So let's do an example. Examples get a little more complicated in modern times. The standard example is take the class and divide them. Say that two people in the class are equivalent if they have the same gender, but that's getting complicated because there are different views on gender. And so, but what you can do though, I mean, what matters is that you pick a definition, all right, and stick with that definition. And if you pick a definition and stick with it, then you can do this, okay? So to be less controversial, let's talk about hair color, okay? So if I pick Sarah and I say I'm going to define the color of someone's hair in this class by asking her to tell me, is that person's hair black, brown, or blonde, or red? 4 colors, okay? It doesn't matter whether you agree with her. That's our definition, okay? I'm not going to ask you to do that. But does everybody understand that you have to have an agreed upon definition, okay? And so that would be our definition. Actually going to ask you, okay? So you don't want to do it? Do I have a volunteer? Do you want to do it? Okay. Okay. What I want you to do is, and again, this is purely your opinion, and nobody's allowed to argue with you, okay? So this is great, right? So now I get, full marks on the question that asks, do I respect student opinions, right? I respect your opinion so much that nobody can argue with your opinion about what color someone's hair is. So I would like you to point out in this class the equivalence class of students. I'm not, I'm always a student. Okay, no, but just in students, okay. What is the equivalence class of all students having brown hair?
These two, him, me, and her.
Okay, right? So you left out some people whose hair you thought was either black, blonde, or red. Okay, and that's fine. That was our definition, okay? So look what she did. She just grouped everybody who is equivalent in terms of hair color. Okay? Now let me ask you this. Again, this is your definition. You had to choose, okay? You had to choose. All right, we won't go through the rest, okay? But if there are some red-haired people in here, they're not going to be called, according to you, they're not going to be called by you brown hair or blonde hair. They're going to be, right, in their own equivalence relation. Equivalence class, excuse me. Okay? So, in fact, what you would eventually do is you would divide the entire class up into smaller subsets, each of which, according to your opinion, which reigns supreme, has the same hair color. Okay? And that's what happens with every equivalence relation. That is, whenever you have an equivalence relation, the set gets divided up into subsets. And the subsets have some important properties, okay? So, and of course, we would have to make sure that you pick somebody as being blonde, or we'd have to throw it out, or red-haired, right? But, so every every single element of the set is going to have to be in some equivalence class. So we want to have a definition so that everybody meets one of those options, okay? So if you declare there are no blondes in the class, we throw that out as an option, okay? So, and the other thing is that if you pick up two of these equivalence classes, right, and this is why we stay away from gender, right? No two are allowed to have the same hair color, okay? There's no overlap there, all right?
I feel like you've gotten in trouble before for using gender.
No. I'm thinking ahead, knowing that that it's complicated, right? You know, I read the same article everybody did in the New York Times, right? So so I just won't go there, right? Because we would have to pick somebody and have that person define gender and who knows what. Okay, right? And then it's a lot less. It's a little more contentious than, you know, disagreeing with Sarah on somebody's hair color, right? Okay, right? Plus we might get into personal questions. I mean, all kinds of issues there, right? And this is the wrong kind of class for that. Okay, so I've just learned how to keep out of trouble, right? So. Okay, so this brings us to the following lemma. This just explains the observation that I just made, that these equivalence classes don't overlap at all. Okay, they're either different or they're the same, or they either don't meet at all or they're exactly the same. Okay, you don't have somebody who's blonde and brown haired, right? Okay, it's almost like a well-defined issue. Okay, so let X be a set with equivalence relation tilde. Then if X bar intersect Y bar is not equal to the empty set for X and Y in X. So that is if they intersect in even a single element, then X bar equals Y bar. Okay, so these equivalence classes really divide things up into sets, subsets that do not ever overlap. If they overlap in the slightest and even a single element, they have to be exactly the same. Everybody understand the statement? By the way, one thing I have learned is that if you bring in something like exciting like gender, even tangentially into the conversation, that people perk up and pay attention, right? So it'll help you guys remember these concepts better. Okay. Okay, there's my assumption. So where am I going to start? Okay, so we're supposing, of course, X bar intersect Y bar not equal empty set. Okay, good. Now what are we going to do? How do we make any progress at this point? Well, we could start by asking, what does that mean?
It means that any element in X bar that is...
You're getting way too complicated. We got a set and we got a set. Their intersection is not empty. What does that mean?
There's an
Element of the intersection. There exists some W, an element of X bar intersect Y bar, right? Okay, we got that settled. Now let's start with the proof. So I'm going to show that X bar equals Y bar. I'm showing two sets are equal. What's my strategy? Show they're subsets of each other. And by the way, is there any material difference here between x and y? Is there anything that's true about one that isn't true about the other? No. So what's going to happen when we do the opposite inclusion? Similar. Okay? Right? This is a clear case of similar because there's absolutely no difference between x and y. We reverse the names and the whole situation stays the same. Okay? And we'll see that that happens because the symmetric law is buried in there somewhere. Okay? So, what's my opening line? I'm always willing to give you the opening word, okay? But I want now the opening line. We're trying to show that this is a subset of that. Yeah, good. You guys don't, you know that you definitely want to not use x or y. And we want to show, of course, that A is over here in y bar, right? Okay, so now let's roll out some definitions, okay? So what does it mean for x to be an A bar? What does it mean?
X is equivalent to.
Yeah, x is equivalent to A. And what do we want to prove eventually? We want to prove that y is equivalent to A, or A is equivalent to y, right? Symmetric law we just throw around at will, okay? Any suggestions about how we might get there? We're going to have to use what we know over here.
Since there exists some W.
Well, we've already got W, so I think I like your since better, starting point. Since W, okay, what's going to be the one we're interested in now? It's in both x bar and y bar.
Yeah, but say it's an X and
X bar, what do we know?
there exists some.
Okay, we don't need any more there exists. We got everything we need, okay? What does that mean? Sorry?
W is equivalent with A.
You're jumping ahead a little bit, okay?
W is equivalent with X.
Yes. W is equivalent to X. And now what?
By the transitive.
By the transitive property,
W is equivalent
W is equivalent
with A.
to A. Okay? And again, we don't care anymore about the ordering since we know it's symmetric, right? But what we've got here is we've got x equivalent to A, x equivalent to W. So A is equivalent to W. Why are we doing that?
Now you do it for W is an element of bar and Y.
Yeah, so we're tying A into this common element of those two. And now we just do the same thing, as Sarah points out. W is an element of y bar, which tells us that W is related to y. So by the transitive law, what do we know?
Y over.
Which, of course, by definition tells us that A is an element of y bar. And then the other direction is similar. Okay, this is one of my favorite problems to put on a test at some point, although now having told you, I may or may not do it. Because I could figure, well, you figure that since I told you I won't do it and therefore you won't study this problem, and then I could put it on there, right? Don't try the psychology thing, right? It never works. Okay, anyway, but you see why. It involves, it is sort of a follow your nose proof, but it's a little bit tricky, right? It's a little bit tricky. All right, so everybody okay with this proof? Okay. So we've proved something actually kind of important about equivalence classes. So let X be a set, a partition P of X is a collection of subsets. I should say non-empty. So this is going to force X to be non-empty also. Of X such that, number one, for every X, an element of X,